Hi, good morning, everyone. We'll wait for 3 minutes and see if any others are joining. All right. So, good morning, everyone. We are going through earthen dams since last two classes. In the first class of earthen dams, we saw about the types of embankments and the causes of failure of embankments. And in the second class, we saw about the different seepage lines and how to identify the seepage lines through the dams. So in the process, we also learned about flow nets, and we derived Laplace equation, and we learned about the concepts of streamlines and potential lines. So in this class, we are going to look at the stability of earthen dams. So before I begin this, I would like to make an announcement that next week I may need to reschedule the class because we are organizing a workshop. So I will not be able to do the class on Monday, but I will let you know the new updated time later. And I also uploaded the tutorial solutions for questions 1 to 4. If you have not seen it yet, you can go through the solutions. And the recordings and the lecture notes so far are also available online. So in this class, we are going to talk about stability of earthen dams, and this would be the last class on earthen dams. In the next lecture, we are going to start on spillways and gates on top of spillways. So today, let's start about the stability of earthen dams. Now, to analyze the stability of earthen dams, in the last class, we discussed about the preliminary section for the earthen dam. So where we would start with the top width of the embankment based on the requirement. For example, if you want to provide a single lane road or a double lane road, then the top width would be fixed according to the requirement. And then the slopes are generally fixed based on the type of soil that you are using for embankment. And the height of the embankment would be based on the upstream water level and the freeboard that you want to provide based on the waves that are generated because of the wind. So considering all of these parameters, you come up with a preliminary section for an embankment. And once you form this preliminary section for an embankment, then we analyze the stability of this section. So once we analyze the stability, if the section is stable, then you can use the section for construction. But if you find out the section is unstable, then you need to revise your design. And we are going to look at the stability considering the failure of the slopes either on the upstream or downstream, where a large mass of the soil might slide off from the embankment. So for example, in this figure, we have the embankment as usual. And what I'm considering is this mass, which is above this dotted blue line, has slid off. So now if this mass is sliding down, then the dam is unstable. So what we would try to do is to estimate the forces acting on this soil mass, which is enclosed by this blue dashed line and the black line, and see if the resisting moments and the disturbing moments are in balance, or if there is higher resisting forces and lower disturbing forces, then the soil mass would be stable. Whereas if the disturbing moments and the forces are higher than the resisting moments, then the soil mass would be unstable. So usually what we do is consider the slip or the sliding of the soil mass to have a circular surface. For example, this dotted line that I am assuming is the surface slip or the surface of slip. So my assumption is that the soil is going to slip along this surface, which is denoted by the blue dotted line. And the method that we are going to do today is called Swedish slip circle method or the slices method, where our basic assumption is the surface of slip is circular. So you have points A and B, which represent an arc of the circle, with O being the center of the circle, and R is the radius of that circle. So if you consider O, then AB would be arc of a circle. Now in this method, first we assume the location of O at certain distance from points A and B. Now we start with this arc and see if this arc is stable or not. If this is stable, then you proceed to construct another arc to consider higher or larger mass of the soil in the embankment and repeat analysis until you consider all the slip surfaces. So this is an iterative process where you have to repeat the process for multiple slip surfaces. And once you consider this slip surface, AB is my slip surface. What we do is to divide this surface into multiple segments. So we have segment 1, 2, 3, 4, 5, and 6. So these are the multiple segments that I have divided the slip circle into. Now each of this segment has a weight component, which is W1, W2 until W6. So if you have n segments, then you would have the weights W1, W2, W3 until Wn. So this Wn is going to act downwards, which is the weight of the soil mass. And we can resolve this weight of the soil mass into two components. So one is normal and the other is tangential. So let's say you have this surface or the slip circle here. So there would be a force normal to this surface, and then there would be a force which is tangential to the surface. So the normal force is represented by N and the tangential force is represented by T. So what we would do is to resolve the weight component into the two components, which is the normal force and the tangential force. So here I'm saying N is the normal component of the weight and T is the tangential component of the weight. And when you resolve it with certain angle alpha, then the normal force would be weight multiplied by cos alpha, and the tangential force would be weight multiplied by sin alpha. Now, if you look at the diagram again, so the normal force would be the resisting force, and the tangential force is the disturbing force. So the moment caused by this tangential force with respect to the center O is T times R. So T is the force and R is the moment, is the distance from the center O. So the moment would be T times R. So if you look at this figure again, so T is acting tangentially at this surface and it is acting at a distance R from O. So the moment would be T times R. So this is the moment due to one individual segment. I'm considering one individual segment, then the moment is T times R. But if I want to calculate the total moment, then you have to sum all the moments due to the individual forces. So R is constant across this arc. So if you consider all the tangential forces, then the distance R is constant. So your total disturbing moment would be sigma TR, or sigma T is the sum of all the forces, T1, T2, T3 until Tn. So if you have n segments, then sigma T would be sum of all the forces. And the resisting force or the resisting shear is created by, so the tangential force is disturbing and the resistance is provided by the cohesion between the soil layers, which is C multiplied by delta L, if you consider delta L is the length of each segment. So the resistance is provided by the cohesion between the soil layers and also the normal force, which is acting with the angle of internal friction of the soil. So this would be your resisting force. And the moment of this force would be R times the force, where R is the distance from center O. So your total resisting moment MR would be sum of sigma n multiplied by tan phi plus C times sigma delta L. So if you have n elements, then sigma n would be n1, n2, n3, and so on until nn. And each of this small arc, if you sum them all up, what you get is this total arc AB. So this length of this arc AB is given by this formula here at the bottom. So the length of the arc AB would be this. So now we know what is the resisting moment and what is the disturbing moment. So we can calculate what is the factor of safety. So the factor of safety is the ratio of resisting moments to the disturbing moments. So the resisting moment is because of the cohesion and internal angle of friction multiplied by the normal force. and the disturbing force is because of the tangential force. So your factor of safety would be this. So this should be more than or equal to 1.5. Now, if you want to calculate what is sigma n and sigma t, you need to calculate n1, n2, n3, and t1, t2, t3, which are both a function of the weights w1, w2, w3, etc. So how do we calculate the weight components? So this is the first segment that we have, segment 1. So if you look at this figure again, so I'm talking about this segment in the bottom, at the toe of the downstream. This is segment 1, segment 2, and we have until segment 6. So your segment 1 is triangular. So even though this is an arc, I'm approximating it to be a straight line of length b, and I'm saying that this is a triangle. Because it is a small segment, we can approximate the arc length to a line, and then this would become a triangle. And you can calculate what is the weight of this triangular element by first calculating what is the volume multiplied with the unit weight. So this is how you get the weight of the first segment. Now the second segment is triangular. So sorry, it's trapezoidal. So I'm assuming that this side has a height y2 and this one is again y1. So if I extend this, so this is segment 1. Now we are talking about segment 2. So segment 1 has a height of y1, and on the other side of the segment 2, I am assuming the height is y2. So this becomes a trapezoid. So you can calculate what is the volume of this trapezoidal area. So similarly, you need to repeat this process until you calculate what is W2, W3, W4, W5 until Wn. So for each of these segments, you need to calculate the weights. So once you calculate W1 until Wn, then you get the normal components and also the tangential components. So the normal component is W times cos alpha, and the tangential is W times sin alpha. So once you calculate n and t, you can get what is the factor of safety. And that is what I am representing here again. The factor of safety is a function of sigma n and sigma t, where you can calculate sigma n and sigma t based on individual weight components. Now, what are the worst case scenarios for both upstream slope and downstream slope? So we need to consider the most critical conditions. So for the downstream slope, the most critical condition is when the upstream reservoir is full. So if this is the embankment, then for this downstream slope, the most critical condition is when the reservoir is full. So since we have the reservoir to the full level, then we would have seepage of water. And if this seepage line is passing through the downstream slope, then there is a potential for this failure of the downstream slope. So that is why the most critical condition is when the reservoir is full. Whereas for the upstream slope, the most critical condition is when there is sudden drawdown in the water. So this is the embankment. Initially, the water is up to this level. So the soil is saturated here, and then you have water pressure acting on the upstream. But if you suddenly release all the water, then the water is going to go down drastically, really quickly. And if you are losing water, then you have the soil is still saturated, but there is no water on the upstream. So what happens is there is excess pore pressure that comes from the soil to the upstream. So because of this excess pore pressure, there is a risk of this upstream slope being failed. So there could be a failure because of this excess pore pressure that builds up in the upstream slope when there is no water in the reservoir. So that is why for the upstream slope, the most critical condition is when there is sudden drawdown in the water. Now, if we consider that sudden drawdown for the upstream slope, or there is reservoir full condition for the downstream slope, then the resisting normal force would be adjusted to consider the pore pressure. So we have the weight that acts downward, and if you resolve that in normal to the arc, then you have an opposing pore pressure that develops. So to consider that pore pressure, you need to update your new normal force, which is N minus U. So based on this new normal force, your factor of safety should also be updated. So here you have sigma N minus sigma U, where U is the pore pressure. So you can recalculate what is the factor of safety for the worst conditions. And again, the factor of safety should be more than or equal to 1 for the worst conditions. Now, so we have seen the failure of the upstream and downstream slopes. Now, the dam has to be stable against sliding horizontal shear. So that we are going to see now, how we can calculate the stability for horizontal shear. Let us say I'm considering this triangular section of the upstream slope. So I'm interested in this triangular section. So which has a height h and width b. And you can do this process for the downstream as well. So even in the downstream, you can consider a vertical line. And you could say this is your region of interest, where you have the pore pressure acting on the other side. And then the resistance would be like this. Whereas on the upstream, the pore pressure is acting towards the upstream, which is from right to left, and your resisting force or the resisting shear is from left to right. So now we want to calculate the balance between these shear forces that are developed at the base and the pressure that is developed in the dam. So the horizontal force that I'm talking about here, which is Pu on this triangular face, would be because of two components. So one is because of the soil, so there is going to be pressure, and then because of the water, there is going to be pressure. Now, this is the force because of the soil. So where you consider the unit weight of the soil, and then the height of the embankment where your soil is, multiply with tan square 45 minus 5 by 2, where 5 is the angle of internal friction. Whereas the pressure exerted by the water is simply gamma h, and the force would be half times gamma h times h1. So here h1, because I'm talking about the seepage line. So this seepage line So the seepage line is starting here and then it is dropping as it enters dam. So the water is only up to a height of H1. So the horizontal force because of the water is gamma H1 squared by 2. So the horizontal force is a sum of these two components, which is because of the horizontal force exerted by the soil and also the horizontal force exerted by the water column. So this is the total horizontal force. That is trying to destabilize the dam, and that has to be resisted by the shear that is developed at the base. So at the base of the dam, you would have resistance that is trying to oppose the horizontal force. And this resistance again is a function of the cohesion at the base of the dam and then the weight of the dam. So the cohesion is acting over an area B multiplied by 1 because we are constrained per unit length of the dam. And then this is the resistance because of the weight. So you have the resisting force, which is given by this expression. So we have the destabilizing force, which is Pu, and the resisting force Ru. So for the factor of safety, you take the ratio of the forces Ru and Pu, and the factor of safety should be more than 1.5. So what we did was to calculate the horizontal force that is trying to destabilize the slope, and then calculate the resisting force that is keeping the slope in place. And then you take the ratio of these two forces, that gives you the factor of safety. And this factor of safety should be more than 1.5. Now, if you consider what is the shear stress at the base, so you have the force Pu that is acting over an area B times 1. So this would be your shear stress at the base because of the force. And the maximum shear stress would be 1.4 times the tau average. So this is the tau or the shear stress because of the horizontal destabilizing force, and the maximum is given by 1.4 times the tau average. And it is assumed that the tau max is going to act at a point which is 0.6 times the width B from the upstream toe. So this is the point where the horizontal shear is going to be maximum because of this force. And at this point, which is 0.6b from the toe of the upstream slope, you can calculate what is the shear stress, the resisting force at that point. So now, instead of looking at the whole base, now we are just looking at an individual point. So at that point, what is the maximum shear force, shear stress, and then what is the resisting stress? So if you take the ratio of this resisting stress to the shearing stress, then you get the factor of safety. So again, this factor of safety should be more than or equal to 1. So far what we did is So what we try to do is to estimate the stability of the slopes of the dam. So first what we did was to check the stability by considering a failure arc. So what we assumed was, if this is our embankment dam, we assume that the failure slope is going to be something like this, which is an arc of a circle. With its center at O, and then this is our point A, this is our point B. So A and B are at a distance of R. And then we divide this arc into multiple segments. So generally these segments would be of same width. So if I say this is B, then this would also be B. This is B, B, again B. Then for each of these segments, we calculated what is the disturbing force. And what is the resisting force. And corresponding to the disturbing force, we calculated what is the disturbing moment and what is the resisting moment. So the factor of safety would be resisting moment by MD. And this should be more than or equal to 1.5. And the second scenario for the failure of slopes is we consider a triangular section and try to calculate what is the horizontal force on it, which is trying to push this soil to the upstream, and this is being resisted by the shear stresses at the bottom. So we try to calculate what is PU and what is RU, and your factor of safety would be RU divided by PU. So this is how we try to estimate the stability of the slopes of the embankment dam. So you can repeat this process for the downstream as well. So assume there is a force here, and then calculate what is the resisting force on the downstream. Or for the slip circle method, you can consider a slip circle surface, something like this, on the horizontal, and then you can repeat the process for the horizontal slope as well. So let's say I did the analysis for this slip circle or the failure arc, and my factor of safety is, let us say, 2. Then I repeat this for another slip circle and see if the factor of safety is more than 1.5. So I repeat it again. So you have to check it for multiple failure arcs so that the slope is stable. So if the slope is unstable or the factor of safety is less than 1.5, then you need to revise the slope. So if your initial slope was 1 in 2 and you observe failure, then you may need to change the slope. So for example, you may need to change it to 1 in 2.5 or 1 in 3. And then repeat the process of this failure arc. And once you do that, then now we will progress on to the stability of the foundation. So we would consider now the shear forces on the foundation of the embankment as well, and see if the foundation is going to be stable or not. So let us say this is our embankment as usual, and this is our foundation. So for embankment, I'm using some soil 1, and for foundation, I'm using soil 2. So there are 2 different types of soil in both embankment and the foundation. Now we want to calculate if the foundation is safe against horizontal shear. So similar to what we did earlier, so I'm considering a triangular element on the upstream slope, and I'm saying P1 is the force acting on this triangle, or the force acting on this total vertical line from the top of the embankment to the bottom of the foundation. So on this total face, the force acting is P1. And then on the left hand side, we have P2, which is acting on this face of the foundation. So now we have two forces horizontally, which is P1 and P2. So the net horizontal force or the net horizontal shear would be the difference between the two lateral thrusts, so which would be P1 minus P2. So this is going to be the net horizontal shear between the two faces, P1 minus P2. Now, we need to calculate what is P1 and P2 individually. And once we calculate P1 and P2, then you can take the difference, P1 minus P2. So P1 is, so either P1 or P2, they are a function of gamma h square by 2 tan square 45 minus 5 by 2. So where gamma is the unit weight of soil, h is the depth, and phi is the angle of internal friction. But since we are talking about two different soils here, then we need to consider gamma equivalent. So gamma equivalent is a function of the gamma of the dam. So you are using some material, soil 1 in dam and soil 2 in the foundation. So now you multiply the unit weight of the dam with the height h of the dam plus gamma dry of the foundation multiplied by h3, which is the height of the or depth of the foundation, and divided by h plus h3. So this will give you the gamma equivalent of the soil. So we are going to use gamma equivalent to calculate the forces P1 and P2. So P1 would be gamma equivalent multiplied by h plus h3, because we are considering the total height from the top of the embankment to the base of the foundation. So this is h3. So h plus h3 by 2 tan square 45 minus 51 by 2. And this is P2. So this is P1, and here we have P2, which is again, we are replacing gamma of the soil by gamma equivalent. And then the height of the soil is h3 in the foundation multiplied by tan square 45 minus 51 by 2. Right. And similar to gamma equivalent, we have to calculate the equivalent angle of friction. So which is given by this equation here. So this is a bit of geotechnical engineering that you may need to revise some of the concepts. So after this lecture, I suggest you that go through the geotech concepts of cohesion, angle of internal friction, and the soil pressure, so that you have a better understanding of what I'm talking here. So you calculate what is the equivalent angle of internal friction, because we are considering two different soils, so soil 1 in dam and soil 2 in the foundation. So we have two different soils. Now, once you calculate the pressure P, then you can calculate what is the toe average or the shear stress. So the shear stress is the horizontal force P1 divided by the area. So earlier we did this, if you remember, the average shear stress is tau equals to Pu by B times 1. So we are doing the same thing here. So P divided by B times 1. So where P is P1 minus P2. And the maximum shear stress is 1.4 times the average shear stress. So we did this earlier. So earlier we calculated the tau average as Pu by B times 1. And then tau max is 1.4 times Pu by B. So we are repeating the same thing to calculate the average shear stress and the maximum shear stress. So now if you want to calculate the factor of safety for this maximum shear stress, then we need to calculate what is the resisting shear stress that is trying to resist this maximum shear stress. So previously we calculated the resisting shear stress based on this, which is a function of cohesion, unit cohesion of the soil, and then you have the unit weight multiplied by the depth of the soil. So we are going to repeat the same thing, but instead now we have two different types of soil, which is for the dam and then which is for the foundation. So the resisting force is an average of the resisting provided by the dam and the resistance provided by the foundation. So you take an average of these two. And once you have the average of the resisting shear stresses, then you take a factor of safety, which is tau F, which is the resisting shear, divided by the average shear. So this has to be more than or equal to 1.5. So again, the maximum shear is going to act at a section which is 0.6 times the width from the upstream toe. So the maximum shear stress is going to be at this point. So at this point, we need to calculate what is the maximum shear stress, which is again a function of the unit cohesion of the soil and then the depth of the soil multiplied by the unit weight. So finally, if you take the ratio of these two maximum shear stresses, that would be your factor of safety. It needs to be more than 1. So if your factor of safety is less than 1, then your design is unsafe. So this is how we calculate the factor of safety for different conditions in the dam. So if you want to analyze the stability, so you need to do the following steps. So first is you need to do the slip circle method. And then check for the worst case conditions. So the most critical conditions for upstream is sudden drawdown, and for downstream is full reservoir level. So you need to check for these most critical conditions, and then you need to check for horizontal shear in the dam, and then you also need to check horizontal shear in the foundation. So if there is a design question on checking the stability of an earthen dam, you need to do all the four checks, starting with the slip circle method. Make sure the dam is stable, the upstream and downstream slopes are stable, and then check for the most critical conditions by considering the pore pressures. And the next step is check for horizontal shear in the dam and the horizontal shear in the foundation. So this is a long process to check the stability of earthen dams, and uh, you need to do this by revising some of the concepts in geotechnical engineering, and you need to go through the lecture notes again to properly understand the concept. So it may not be all clear in one lecture, but if you read the notes again, it might become clear. So we will solve a problem on the stability of earthen dams in one of the tutorials. So not this week, but next week we will have a tutorial in which we will try to solve the stability of an earthen dam. So that would be the end of earthen dams. And in the next lecture, we will do um, the last topic, which is spillways. So in spillways, we are going to see the different types of spillways, and we are going to design spillways. We are going to see energy dissipation below the spillways, and the types of gates on spillways, and probably the design of gates as well. So all of this we need to cover in the remaining lectures. So the next week tutorial is going to be on earthen dams, and the following lectures would be on spillways. And as a reminder, the next week's class would be rescheduled. I will let you know the time later. But so this is what I have for today's lecture. So any questions on this? So any questions on this topic so far? So if there are no questions, then I'm going to close the session. I will upload the lecture notes and the recording on Google Classroom as usual. You can go through the lecture notes. All right. Thank you. I'll see you in the next lecture. All right. I'm going to close the class. Yeah. Thank you.